All right, so listen, today what I want to talk about is something that's more conceptual. We've been sort of talking nuts and bolts, and today, practical stuff, interpretive stuff. And today I want to talk a little bit more about how some stuff works in NMR spectroscopy. It's not going to be anything too fancy, and it gives you a little perspective on my take and understanding of NMR experiments, which is very different, say, than Professor Shaka's take or interpretation or Professor Martin's take or interpretation. These are NMR development people, and my group and you will be users of NMR spectroscopy as a research tool. But one of the things is you can't just take NMR as a black box. As you're already seeing when you're going down using the instrument, you kind of have to keep your head about you. Oh, what am I doing? Why am I locking it? Why am I shimming it? What's the shimming doing? What does it do if I don't do this? And what I'd like to be doing is giving you a feel for some parameters and things that you may not be understanding in spectra. So we've already, for example, had instances where people look at their own depth spectra and say, wait a second, why do I see in the depth 90 a little peak for, say, a methyl group or a little peak for a CH2 group? And a lot of this has to do with parameters, and so that's what I want to give you a feeling about. We're going to start with one experiment that's kind of like a depth, but a lot less fancy, and I think it's one that's easy to understand. It's called the APT, so it was a precursor. That stands for Attached Proton Test. And the more NMR spectroscopic name for the technique, which actually is going to make a lot of sense to you when we start to talk about how it works, is called the J-modulated spin echo technique. And then we'll talk a little bit about depth. We won't go and understand it as well, but you'll see how the parameters that we talked about for the APT relate to the depth experiment. Depth, if you don't know, is distortionless enhancement by polarization transfer. From a practical point of view, what the depth does, as you all know, is allows you to identify the CHs, CH2s, and CH3. So in other words, the methynes, the methylenes, and the methyl groups. And what the APT does is it's a less sophisticated experiment. It gives you your Cs, your quats, and CH2s and distinguishes them. So I'll say distinguishes, let me maybe put it that way. Quat and CH2 from CH from your methine and methyl. So in a way, the depth experiment is more of a litmus test experiment. So we're going to start to get a feel for complex pulse sequences. I'm going to introduce some concepts like the rotating frame and the effect of various pulses. We talked a little bit about this when we introduced NMR spectroscopy. And we'll see a spin echo experiment. So I just want to review some of the spin physics that we learned when we started to talk about NMR spectroscopy. So remember, you start and you've got this difference in population between the alpha and beta states, and that leads to a net magnetic vector along the z-axis. And remember, that vector is a bunch of vectors that are precessing. And we talked before about the concept of applying a 90-degree pulse. So remember a 90-degree x pulse, and you think about the right-hand rule, that means you have a coil along the x-axis. You're applying essentially a force onto the vector, which is bringing the vector down into the xy plane. And it brings it along the y-axis. Now remember what that means. Having the net magnetization in the xy plane means that we've now equalized the alpha and beta state populations. By having a differentiated population of alpha and beta states, you have net magnetization along the z-axis. But when the alpha states are equal to the beta states, then you have no net magnetization along the z-axis. What you do have is magnetization on the xy plane. And because you've done this as a pulse, all of your vectors start out initially along the y-axis, and then remember you have your precession that leads to motion in the xy plane of the vectors, and that gets picked up by the coil and gives you a cosine wave that when you Fourier transform gives you a peak. So the other pulse I'll give you an idea on is, just remember, if we apply, instead of a 90-degree pulse, a 180-degree pulse along the x-axis, now that flips the population of the alpha and beta states. So instead of dragging the magnetization down into the xy plane, you've dragged it all the way along to the negative z-axis. I'm trying to represent things in 3 dimensions here. And so that brings our magnetization to the negative z-axis. And if you think about it, this means now that you've inverted the population of alpha and beta states. So if we had more nuclei in the alpha state than the beta state before, then after, or more nuclei in the spin up, in the spin down state, if you've had more nuclei in the alpha state than the beta state, you flipped the population over here. So that's basically all the spin physics that we need to get to a point to really think our way through an experiment that ultimately is going to allow us to distinguish our quats and our methylenes from our methyls and methynes. And so now I want to sort of develop that idea. And so let's take this situation here, and I'm just going to project the xy plane into the plane of the blackboard because it's going to help us to look down on the system rather than for me to try to keep making these horrible 3-dimensional drawings. So okay, so here we are in this situation where we've got our x-axis, we've got our y-axis, now we're looking down the z-axis, and we have our magnetization along the y-axis. Now remember, the magnetization along the y-axis is precessing. And so if you just think of this as a single line, it's going to precess at an angular velocity omega. So like if it's 500 megahertz, you're going to have precession at 500 million times per second in the xy plane. That says angular velocity if you're interested. It's just my way of representing that it's moving. So in other words, as you wait, if we're precessing around in the xy plane, as you wait some time t, now when we look at the xy plane, now your vector is over here, and it's continuing to precess. Remember, this is what gives rise to your signal. That's your FID, where you get this cosine wave over here. That's basically the coil picking up your processing vector and generating electricity, generating alternating current in the coil that ultimately you amplify, use the analog to digital converter on, and then Fourier transform. All right, what I want to do at this point, though, is to introduce a concept that NMR spectroscopists use to make their lives easier. And the idea is the rotating frame. And it's basically saying, let's just have our axes processed for conceptual purposes. It actually works out for the detection purposes with various electronic techniques. But let's have our axes rotate at the angular velocity. So that means we'll have the axes rotate at omega. And so we'll have our rotating frame, and we'll call that x prime, y prime. So now, if you think about it, if you're in the rotating frame, if your frame is rotating, your frame of reference is rotating with angular velocity omega, and we wait time t from the rotating frame, how does our magnetization look at time t? Exactly the same. And that's the whole big concept of the rotating frame, is simply we go ahead and we adjust so we're not spinning around at 5 million times per second. All right, now we're ready to introduce the concept of the spin echo. And that's going to be the basis for differentiating our methanes and methylenes, our quats and methylenes from our methanes and methyls in the depth experiment. Okay, so the idea behind the spin echo is as follows. We're going to be in the rotating frame, and so we start with a 90-degree pulse, and I'll call it a 90-degree x prime pulse just to show that we're working in the rotating frame. And imagine for a moment now that I have some vectors and they start along the y prime axis. But now let's say for a moment that some of those vectors are moving a little bit faster than the Lamour frequency, than the velocity omega, and some of them are moving a little bit slower. So in other words, we've got our frame rotating at 500 million cycles per second, but some vectors are going a little faster, and some vectors are going a little slower. So now, if you imagine on this thought experiment that you wait time t, now what's going to happen after time t, after some time to those vectors?
The ones that are rotating slower will appear to go clockwise, and
the ones that are rotating slower will appear to go clockwise, and the ones that are going, I think, yeah, right, clockwise and counterclockwise. So now our vectors are going to fan out with respect to the rotating frame, and those that are going one direction are going to be going this way. I think it's actually counterclockwise in this axis system. But the point is that they're diverging in velocity. So now we've got some that are headed this way, some that are headed this way. Now imagine for a moment we now, at this point after time t, apply a 180-degree x prime pulse. So in other words, now we do the same thing that we did before, and we apply a 180-degree pulse. Now, when you do that, again, just think right-hand rule. And remember, any component of your magnetization that's along the x prime axis, when you apply a pulse to it, right-hand rule, doesn't do anything. Any component of your vector that's along the y prime axis flips over 180 degrees. Does that make sense? So when we take this vector and we apply our 180-degree pulse, the y prime component comes on over to the negative y prime. Like so. And we do that to all of these different vectors, and they've all flipped around the x prime axis. They've all gone to the negative y prime axis, and yet they are still processing at the rotating frame, but now they're headed inwards. And that's the key to this whole thing. So because they're still going in the same direction, these ones a little bit faster, these ones a little bit slower than the rotating frame, they converge inward. And if we wait another time t, that same time increment, so I'll say t again, now what's our picture at this point? They're all on the negative y-axis. So they are all like so along the negative y-axis. And this is the basis for many, many sorts of NMR experiments. This is called a spin echo. And one of the reasons that people invariably do spin echoes is, in addition to what we're talking about here, which I'll show you in a second, which is J modulation, you've also got T2 relaxation, where vectors fan out in the xy plane. And what the spin echo experiment does, what the spin echo does, is a refocusing of those vectors. So the ones that are inadvertently, due to T2 effects, moving a little faster, and the ones that are moving a little slower, by applying this 180-degree pulse halfway through, they refocus. And so almost every experiment you see, the ones I'm talking about now, but also 2D experiments, are going to involve some sort of thing that involves a weight and then an equal weight. So if I write out this simple pulse sequence, what it is we apply a 90-degree pulse, we wait, we apply a 180-degree pulse, we have an equal weight, and at that point, the spins refocus. And so if you've already started to notice as you're working some of the 2D experiments, there are various delays. And you may see this in the handout about various delays. Some of the delays you've learned about in the 1D experiments may be relaxation delays, where it's just for your magnetization to return to the z-axis. I think that's what's D0 or D1 on our instruments. But then some of the other delays that you're choosing are specific parameters related to this. All right, as I said, this now sets us up for the so-called J-modulated spin echo experiment, or APT. All right, so now we're going to bring in the idea of two different channels. Now, the experiment here is a carbon-detected experiment, and so we're going to be doing stuff in the carbon channel. Remember, normally when you're running a carbon-13 NMR, you're proton decoupling. And the reason you're proton decoupling, remember all those coupling constants I talked about, the J1 CH being like 125 hertz, and the J2CH being like 10 hertz. So if you took an undecoupled spectrum of ethanol, it would be horrible, because your CH2 group would appear as a quartet that was then split into a triplet. So it would be a quartet of triplets, and your CH3 group would appear as, your CH2 group would appear as a triplet of quartets, and your CH3 group would appear as a quartet of triplets. So imagine how tiny your peaks would be, right? Because a singlet is this tall, a doublet is half as tall, a quartet is 1 to 3 to 3 to 1, where the total height is the same as the height of the singlet. And if you go now to a quartet of triplets, everything is split. Well, you've already seen when you collect your carbon-13 that you're fighting noise on this, so you'd be horrible. So we always end up collecting these fully decoupled, proton decoupled experiments, proton decoupled spectra. So the trick in the APT is we're going to turn on our proton decoupling partway through the experiment. So we do a 90-degree X pulse, and I'll call it X prime pulse because we're in the rotating frame. And then we're going to wait 1 over J, 1 over the coupling constant. And then we're going to apply a 180-degree pulse. And meanwhile, we're going to start to do stuff in the proton channel. So for this point, we haven't been proton decoupling. We're going to, at this point, turn on the broadband decoupler. All right, remember, when you apply a broadband decoupler, what you're doing is rapidly flipping the spin states of the proton. So that's going on at 500 megahertz. Meanwhile, you're applying these pulses at 125 megahertz for the carbon. So now you're going to be rapidly flipping the spins on the protons. That's why you normally get a singlet. But here we've done something first where we haven't immediately turned on the broadband decoupler. We've applied our 90-degree pulse. We're waiting 1 over our coupling constant. We're then going to go ahead and apply another, we're going to wait another 1 over the coupling constant. And then we're going to observe all the time with our broadband decoupler going on. And this is, as I said, what's going to lead to the CH3s and CH2 and CHs up, and the CH2s and the Cs, well, we'll say the CH2 and the Cs are down. All right, so let's think about what each of our carbons sees. So if you have a quat carbon, we can conceive of that quat carbon as being a peak at the line at the frequency omega. In other words, the quat carbon, because the rotating frame, as I said, is partially an artifact, it's partially a conceptual tool, it's partially an electronic tool. So let us conceive of the rotating frame as being exactly tuned to the frequency of the carbon. So in other words, in the rotating frame, you're going at omega, which means here you're going to be going at 0. OK, now imagine a methane, and we're only going to be considering one bond coupling. So a methane is going to be, without decoupling, it's going to be a doublet that's centered around this frequency omega. So you've got one line of the doublet is going to be going faster. And think about it. Remember, the J is the coupling constant, so the separation is J. So you're going to be going at omega plus J over 2. And here, this other line is going at omega minus J over 2. Does that make sense? Now, if you have a methylene, now you have, without decoupling, a triplet, a 1 to 2 to 1 triplet. And remember, the separation of the lines is J. So the center line is at omega. And the line, the downfield line, is at omega plus j, and the upfield line is at omega minus j. And we'll do the same thing now for a methyl group. And in a methyl group, now you have 4 lines in a 1 to 3 to 3 to 1 ratio, centered around omega. And so what's the position of the line I just drew the arrow to? Omega plus 1/2 j. And the position of the next line? Plus 3/2 j, right? And the other big line? Minus j over 2, minus 1/2 j. And the last small line? Minus 3/2 j. All right, 3j over 2. All right, that sets us up now to start to consider the different scenarios. And we'll just consider the quat, the methylene, the methane, the methylene, and I think by the point you get to the methyl, it'll all sort of make sense. All right, so let's try this scenario for a quat carbon. We apply our 90-degree X prime pulse, so we're in the rotating frame. Our magnetization ends up along the Y prime axis. We weight 1 over j. So if j is 125 hertz, you would imagine weighting 1/125th of a second. And how do things look after 1/125th of a second? Same, yeah, because we don't have any J coupling and our rotating frame is going right at omega. So after 1/125th of a second, after 1 over J, nothing happens. Now we go ahead, we apply our 180-degree X prime pulse, and at the same time we turn on our broadband decoupler. If there had been coupling, in other words, if the carbons attached to a spin-up proton were precessing faster, and the carbons attached to a spin-down proton were precessing slower, now when you turn on the broadband decoupler, you're flipping back and forth, and they're both precessing at the same angular velocity omega. But here we don't have any attached protons, so we don't even change that coupling thing. OK, so at this point, you go ahead, and now your scenario looks like this, where now your magnetization is along the negative Y prime axis. And then you're again going to weight 1 over J. So again, we're weighting 1/125th of a second if we're using this value of J is equal to 125 hertz. And so now, after 1 over J, how do things look? Same. And so at this point, our magnetization is along the negative Y prime axis. That means if you're not in the rotating frame, you're a cosine wave. But remember how I've typically shown our cosine waves like this, where we start positive? If your cosine wave starts negative, which is what happens when your magnetization is along the negative axis, the Fourier transform is a negative peak. So here, when we Fourier transform, we get a negative peak, a line down. All right. Remember, the APT is going to be distinguishing our methynes from our quats, or should I say, our methynes and our methyls from our quats and methylenes. So now let's try this exact same scenario, but we're going to try it with a methine. All right. So now, and I'll just write things out exactly the same way. We apply our 90-degree X prime pulse. We end up with our magnetization. Got to make my axes a little bit bigger here. We end up with our magnetization along the Y prime axis. But now we're processing, and remember we said one of them is processing at J/2 relative to the rotating frame, and the other of them is negative J/2. So I guess our rotating frame rotates counterclockwise. And now we're going to wait 1/J. So how do things look at this point after 1/J? 45 degrees. Everyone in agreement? So let's put this in concrete numbers. Let's say we're at 125 hertz is J. In other words, our angular velocity is going around for J is going around 125 times a second. But we're going around at J/2, so we're going around at half that angular velocity. So in other words, if you wait 125th of a second, where do you get to? 180. So you get to the negative Y prime axis. And that's the main point over here, is now your two vectors, both the one attached to the one processing faster due to being attached to a spin-up proton, and the one processing slower due to being attached to a spin-down proton, they've come by on the negative y-axis. Now, at this point, we go ahead, we apply our 180-degree X prime pulse, and we turn on our broadband decoupler. So after you've applied your pulse, your magnetization is along the Y prime axis. But you've just turned off your J coupling because you've turned on your proton decoupler. So now you don't have two separate vectors, one processing faster and one processing slower. They're both processing at the Lamar frequency. In other words, they're staying along the positive y-axis. So now we go ahead and we do this whole shebang again of we wait 1/, I guess, where am I in my drawing? OK, so we wait 1/J, but nothing happens. Except, remember what I said about T2. Remember what I said about defocusing. The reason you're doing this is to refocus any inhomogeneity in the spins due to T2 relaxation. But nothing changes in regards to this primary picture. Now you're decoupling. Your magnetization is still along the positive y-axis. And so at this point, when you observe, what do you get? You get a positive peak. Right, this translates into this situation here where you have a positive cosine wave instead of a negative cosine wave. And the Fourier transform of a positive cosine wave is a positive peak. So you can see how we've differentiated our methynes from our methylenes by way of this spin echo experiment. Our methynes from our quats by way of the spin echo experiment. Let's move on to our methylenes at this point. All right, so our methylenes now you can think of as being composed of 3 different vectors. So you've got a vector that's going at omega, and a vector that's going at omega plus j over 2, plus j, and a vector that's precessing at omega minus j. So we apply our 90-degree x prime pulse. You end up with the situation where you can think of this as 3 vectors comprising your triplet. One of these is going at omega. One of them is going at omega plus j over plus j. And the other of them is going at omega minus j. And of course, in the rotating frame, you just forget about the omega, right? Because the whole system's going at omega. So you've got one of them going at plus j, one of them going at minus j. I guess if I'm doing parentheses, I'll put my parentheses around the omega here. All right, so again, now we're weighting 1 over j. And if you can think about it, what does it mean if you weight 1 over j? They're all on the positive y, because you weighted your 125th of a second or whatever it is, and everything has come back over to here. And at this point, you go ahead and you apply your broadband decouple and your 180-degree x prime pulse. That flips your magnetization over to your negative y-axis and recombines it. And again, you weight 180, you weight 1 over j. And now nothing happens because you've turned on your broadband decoupler, except any refocusing due to of the T2 relaxation that's occurred. So after 1 over j, your scenario is still a negative peak, and so you get a negative peak over here.
Relaxation is spin lattice.
Spin lattice relaxation. So invariably, you're always fighting spin lattice relaxation. Remember, that's the defocusing in the xy plane. And so a lot of the pulse sequences incorporate these spin echoes to bring up the intensity and sharpen things back up. And so that's why, because if you looked at this and you said, well, why are you doing the second half of the experiment? Why don't we just turn on the broadband decoupler and observe? And the short answer is, well, yeah, it would work. It just wouldn't work as well. Your peaks would be less intense. You'd have more artifacts and so forth. So the spin echo gets incorporated. And it gets incorporated into all of the experiments that we won't go into a lot of depth on, like the HMBC experiment, where we're going to use it but not necessarily understand it quite as well. All right, let me show you one of these experiments. The APT is written up in Phil's handbook, so you can actually use it, but in practice you'd have no reason to use it versus the more modern depth experiment. I just like this because I think it's something that we can easily wrap our heads around for starters without too much mental gymnastics. All right. So this is one I pulled from the supplemental book Freibel, and it's just an example. It's a sugar molecule. And this particular sugar, they ran an APT experiment. So here you have a regular C13, and then you have, so this is, of course, your H1 decoupled. You always run H1 decoupled these days, C13 NMR. And here's your APT experiment on the sugar. And so you'll notice in the sugar that carbon 2, which is this quat, is, whoops, carbon 2 is down over here. And this carbon here, which is the methylene out here, it's carbon 9. That one is down over here. And then you have one more down, and that one more down, if you notice, there's this methylene hiding out at position 3. So you have 2, 9, and 3. The methynes and methylenes are all down. All right, let's at this point, let me raise the 180-pound gorilla in the room that should be bothering you, and you've seen this, and some of you have found it confusing on the exam, and that's the issue. That's the issue of what is J. Because the problem is, of course, you're going to do one experiment, and so you have to choose an average J. So as I mentioned before, for an sp3 CH, J is typically, J1 CH is typically about 125 hertz. For an sp2 CH, remember the degree of coupling is intimately linked to the hybridization of the carbon, because that tells you how much time the electrons spend near the nucleus, right? If you have more S character, if you have 33% S character, those electrons are spending more time near the carbon nucleus than if you have only 25% S character. So you get a bigger coupling constant. So the J1CH is about 160 hertz. So normally you go ahead and you say, all right, you compromise and you use a middle value of 100, let's say 140 or 145 hertz. And you say, all right, that's pretty good. You can get away with that largely. But now imagine a situation where you have something unusual. So I'll say, but what does that do for something where you have a J1CH of 250 hertz, like an alkyne? And in an alkyne, you'll look and you say, wait a second, everything's going to be screwed up. Because while you're waiting your 125th of a second or 140th of a second, and your CHs, your sp3s and your sp2 CHs are doing exactly what you expect, your alkyne CH is zipping around and processing twice as fast. So what does that mean when you're looking at your data? That means you look at the alkyne CH and you come up with exactly the wrong conclusion about, or a conclusion, or a completely ambiguous thing where you see a peak in one spectrum and a peak, peak up. Well, we'll get to the depth spectrum, which is where it really counts. But in other words, the APT, if it's going around twice as fast, you'll come to the wrong conclusion. So alkynes end up being oddballs in many, many of these experiments, not just in the APT, but also in the depth, and then in the HMQC as well, which also relies on these types of things. And that's an important take-home message. The other one, somebody, I forget who raised this question, it was a good question over the homework, was saying, well, do you ever see, and it was something, it may have been depth, do you ever see J2CH? And I'm saying, well, no, they're usually very small. It's like 20 hertz, and 20 hertz is nothing. Well, so we had, I don't know if people, I guess about 7 people took this on the exam. And took this problem. And sure enough, and I put an X over it, but you may remember in the depth, this peak actually showed up and I'm like, what the heck is going on? I just put an X on it to help you out on this. But I was just looking, and it turns out in this situation, J2, right? You've got all this SP character. J2CH is equal to 50 hertz for an alkyne. So again, you're going to get anomalous coupling. In other words, that's this coupling from this hydrogen over to this carbon. So none of these experiments are litmus tests that you can use without really engaging your mind and thinking about what's going on. I guess another one I've mentioned earlier is chloroform, because electronegative atoms can have a big effect on coupling constant 2. And in chloroform, J1CH is equal to 208 hertz. So in other words, even though the carbon in chloroform is formally sp3 hybridized, because you've got 3 electronegative atoms attached to that carbon, your J1CH is a lot bigger than 125 hertz. It's 208 hertz. All right, so the depth experiment ends up having the same types of issues here. Because you have to use an average J value, your depth experiment is not necessarily going to be perfectly clean. And so you're going to be looking and saying, okay, well, I see this peak as having a positive peak in the depth 135 and a teeny positive peak in the depth 90, but I know that that's not a real methane because it's just a little bit of the inaccuracy of choosing an average J value. So you're always making these judgment calls. All right, let me take a moment. I'm going to show you the depth pulse sequence and tell you what it does without necessarily walking through the spin physics. So as I said, it's distortionless enhancement by polarization transfer. And the polarization transfer really is the key part. So remember, carbon has 1/4 the magnetogyric ratio of proton, which means the Boltzmann differential in population is about 1/4 as big for carbon as it is for proton. Carbon is a very insensitive experiment. You've got 1% C13, 99% C12, which is spin inactive. There's nothing you can do about that. You're only detecting what's associated with your C13, but then you're damned and damned and damned again by the fact that the magnetogyric ratio of carbon is 1/4 that of proton, because your Boltzmann distribution is 1/4 as big, your vector is 1/4 as big, it's processing 1/4 as fast, and each of those goes to 1/4 of 1/4 of 1/4 of the signal that you get for proton. And then you throw that on top of the 1%, and you're down at like 1/5700th the signal. Okay, so what the polarization transfer does is it flips the population of the proton and the carbon. So the carbon, in the end, through this pulse sequence, gets the bigger Boltzmann distribution of the protons. Let me just show you the pulse sequence and tell you the things that it does. All right, so here's in your proton channel, you actually start out. You apply a 90-degree X prime pulse. you wait 1/2J, you apply a 180-degree X prime pulse. In the meantime, you start doing things in your C13 channel. So at that point, concurrent with applying a 180-degree X prime pulse in the proton channel, so that's at like 500 megahertz, you're applying a 90-degree X prime pulse in the carbon channel, which is like 125 megahertz. Now you wait another 1/2J. Now you apply a pulse, which I'll show you in a second. We'll call that a theta Y pulse. Your theta, or I guess I'll call it theta Y prime pulse. That one's going to vary. You'll do 2 or 3 experiments. So I'll say 2 or 3 experiments. I'll put that in parentheses for or 3. So while you're applying the theta Y prime pulse, you'll apply a 180-degree pulse in your carbon channel. Doesn't matter if it's X or Y that you're applying. You again wait 1/2J. And now you go ahead and you finally turn on your broadband decoupler and you acquire. And this sequence of pulses leads to both the polarization transfer, and it's also going to lead to differentiation of our methynes, methylenes, and methyl groups. So if you apply a theta Y is equal to 135 degrees, your CHs and CH3s end up being positive, and your CH2s are negative. If you apply a theta Y prime pulse of 90 degrees, then your CHs are positive. And some people will do an experiment. So this is, of course, called a depth 135. And this is called a depth 90. And some people will do a third depth experiment where they do a theta Y prime pulse of 45 degrees. And in that experiment, you end up with your CHs, CH2s, and CH3s all positive. And you look at that and you say, what's there to gain? Because all of that information in the depth 90 and the depth 135 is redundant with the information the depth 45, or to put it another way, the depth 45 is redundant. But what you can do is you can add and subtract your spectra to get subspectra. So you can do what's called spectral editing to give your CH, CH2, and CH3 subspectra. Let me just show you what I mean. Imagine for a moment that we go ahead and take our depth 45, in which all of these guys are positive, the CH3s, the CHs, the CH2s, and the CH3s, and we subtract from that the depth 135, in which the CHs are positive and the CH3s are positive and the CH2s are negative. Well, you subtract a positive number from a positive number, you get 0. You subtract a positive number from a positive number, you get 0. You subtract a negative number from a positive number, and you get a bigger positive number. So you go ahead, and when you do that subtraction, you get a spectrum in which your CH2s are the only thing that shows up. You do other subtractions, you can get one that you have a just your CH3s or just your CHs. In practice, it doesn't work so well, and it's messy. And given the fact that it's really no big deal to stare at your depth 35, 135, and stare at your depth 90, people generally don't do it, but you can do it as well. Anyway, that pretty much sums up what I want to say. So the main take-home message is in all of these pulse sequences, you're making choices about delays that are based on coupling constants. And if those choices, they're always compromises, they're always estimates, if those choices don't match your molecule, you will get confusing results, which means always be careful in interpreting your spectra. And when you're collecting your spectra, pay attention to those parameters that Phil talks about because they actually have meaning.